For 480-volt systems, the most reliable testing method is the three-point method, also known as the fall-off potential method. This is particularly important in areas with very dry soil, where soil resistivity is high. The three-point method involves injecting a known current into the ground rod under test. To perform the test, firstly, disconnect the grounding electrode conductor from the grounding electrode. This is crucial to isolate the grounding electrode's resistance. Secondly, insert a test rod, often called a current electrode, into the soil at a distance of approximately 100 feet from the grounding electrode. Thirdly, insert another test rod, referred to as the potential electrode, into the soil midway between the grounding electrode and the current electrode. Fourthly, connect the test equipment to the grounding electrode, the current electrode, and the potential electrode. Fifthly, inject a known current between the grounding electrode and the current electrode. Sixthly, measure the voltage drop between the grounding electrode and the potential electrode. Seventhly, calculate the resistance using Ohm's law, where resistance equals voltage divided by current. The key advantage of the three-point method is its ability to provide accurate readings regardless of soil conditions. The injected current creates a voltage gradient in the soil, and the potential electrode measures the voltage drop at a specific distance. This measurement is less susceptible to variations in soil resistivity, making it reliable even in dry soil. In contrast, the clamp-on-ground test method relies on measuring the current flowing through the ground rod using a clamp-on ammeter. While this method is convenient, it can be less reliable in dry soil conditions. The reason is that high soil resistivity can significantly affect the current readings. High resistance in the soil can reduce the current flow, leading to inaccurate measurements. Furthermore, the clamp-on method assumes that all ground paths are equally conductive, which may not be the case. If there are multiple ground paths with varying resistance, the clamp-on meter may not accurately reflect the resistance of the grounding electrode itself. It's also important to understand the factors affecting soil resistivity. Soil resistivity depends on several factors, including moisture content, temperature, and chemical composition. Dry soil has significantly higher resistivity than moist soil. Temperature also affects resistivity, with colder temperatures generally increasing resistivity. The presence of salts and minerals in the soil can lower resistivity. To ensure accurate testing, it is essential to consider these factors. When performing the three-point method, ensure that the current and potential electrodes are placed at appropriate distances from the grounding electrode. The distance between the electrodes should be sufficient to minimize the influence of the grounding electrode's resistance on the voltage measurement. Also, use high-quality test equipment that is calibrated regularly. Check the equipment specifications to ensure it is suitable for the voltage and current levels being used. In addition to the three-point method, other variations can be used to improve accuracy. One such variation is the four-point Wenner method, which uses 4 equally spaced electrodes to measure soil resistivity. This method is particularly useful for determining the optimal location for grounding electrodes. Another important consideration is the National Electrical Code, or NEC requirements for grounding. The NEC specifies the minimum requirements for grounding electrode systems, including the size and type of grounding electrodes, as well as the bonding requirements. It is important to comply with the NEC to ensure the safety and reliability of electrical systems. NEC Section 250.52 covers grounding electrodes. Grounding electrodes must be of specific types, such as metal underground water pipes, metal frames of buildings, concrete encased electrodes, ground rings, and rod and pipe electrodes. NEC Section 250.53 provides requirements for the installation of grounding electrodes. Rod, pipe, and plate electrodes must have at least 8 feet of contact with the soil. The upper end of the electrode must be driven below the surface of the earth. NEC Section 250.66 covers grounding electrode conductors. The size of the grounding electrode conductor depends on the size of the service entrance conductors. Table 250.66 provides the minimum size of the grounding electrode conductor for different sizes of service entrance conductors. NEC Section 250.166 covers sizing the grounding electrode conductor for alternating current systems. The size of the grounding electrode conductor is based on the size of the service entrance conductors or the equivalent size for parallel conductors. Always refer to the latest edition of the NEC for the most current requirements. For example, consider a 480-volt system with a 400 amp service. According to NEC Table 250.66, the minimum size of the grounding electrode conductor for a 400 amp service is typically No. 3 copper. However, always consult the specific NEC table for the most accurate information. To further enhance safety, consider using ground fault circuit interrupters, or GFCIs. GFCIs are designed to protect against electrical shock by detecting small ground faults and quickly interrupting the circuit. GFCIs are commonly used in wet or damp locations, such as bathrooms and kitchens, but can also be beneficial in industrial settings. Also, regularly inspect grounding systems for corrosion and damage. Corrosion can increase the resistance of grounding connections, reducing their effectiveness. Damaged grounding conductors or electrodes should be replaced immediately. Proper grounding is essential for protecting equipment and personnel from electrical hazards. A well-designed and maintained grounding system provides a low impedance path for fault currents, allowing protective devices to quickly clear the fault. This reduces the risk of electrical shock, fire, and equipment damage. In summary, for 480-volt systems, especially in dry soil conditions, the 3-point method is the most reliable testing method. It provides accurate results regardless of soil resistivity variations. While clamp-on methods can be convenient, they are less reliable in dry soil. Proper grounding is crucial for safety and should be regularly inspected and maintained. Following NEC requirements and using appropriate testing methods ensures the effectiveness of grounding systems.